In this session, we will discuss about influence line diagrams. Right? So, these are very interesting and important diagrams, especially when problems with moving loads are considered. Okay, so I mean, it doesn't mean that it will consider dynamic analysis. It is still all static analysis. But imagine, there is a bridge from one side to the other. There is a vehicle which is crossing, and this bridge is supported on multiple piers, right? So we may be interested in asking a question that, as a vehicle moves from one end to the other end, at which point of time or at which location of the vehicle uh, does one peer experiences the highest moment, right? So that kind of a question one may ask. And influence line diagrams are a way to answer that type of question, right? So, by definition, influential line diagram is a diagram or a graph, okay, so that represents the variation of a particular force response, okay, either a force response of a system or displacement response of a system, right? So, force responses can be, let's say, support reaction, it can be shear force at a section, it can be bending moment at a section, it can be axial force at a section, right? So, these are the force responses of a system, or a displacement response, which can be, let's say, slope or deflection of the structure, right? So a diagram that represents the variation of a particular force response or displacement response at a specified location or position of a structure, okay, uh, for different positions of a unit load on the structure, okay. So the location where we are interested in the response of force or displacement, that location is fixed, okay. So a specified position of a structure, okay, but the location of the load is variable, okay. And in this case we consider a moving unit load, okay, with the idea that, in case it is a non-unit load, it can be simply scaled, right? So if the response due to 1 unit force is known, response due to 20 unit force would be just 20 times that, right? Because we are using linear analysis, these can be scaled, okay. I think the only thing to remember is that the unit load is passing, that is a moving load, okay. The location of interest is fixed, okay. So we may say a bending moment at midspan, or shear force at L by 2 or L by 4, right? So those locations are fixed, but load goes from one end to the other throughout, okay. So in this case, the ordinates of the graph will give the value of the response at the specified location, okay, for a given position of the load on the structure, okay. So this is, as I said, this is very useful in analyzing systems with moving loads, for example, vehicles passing on a bridge, okay. And just to emphasize, this note is there that it doesn't consider dynamic effects. It only does static analysis. The analysis is static, okay, just that we consider different positions of the moving load, okay. So let's look at a few examples. Let's say there is a simply supported beam which is given like this AB, okay, and we consider making influence line diagrams or ILDs for different quantities of interest, okay. So in the so what we will do is we will consider the structure with a unit load at a variable position x, okay. So this position x is actually the variable, right? So all the graphs are going to be made with respect to this position x, okay. So in the graphs that we make, the abscissa or the x-axis will actually be this x, which is the location of the unit load on the structure, okay. Okay, so let us say we want to make the influence line diagram for VA, or vertical reaction at A, okay. So in this, the position of interest is at x equal to 0, and that is fixed, okay. Position of interest is A, and we are interested in VA, the vertical reaction at A, okay. The position of the unit load is variable, and that is considered at an arbitrary distance x from A, or from the one of the ends of the structure, right? Now, in this case, it is fairly straightforward. So, VA can be found out in terms of X by simple force balance, right? And then we can make a diagram which is shown here, where the ordinate gives reaction at A. Okay, so this vertical axis is giving reaction at A, VA, and the horizontal axis X gives the position of the unit load. Okay, so basically, we may want to ask a question that uh, if there is a 50 kilonewton load applied at midspan for this beam, what is VA? Okay, so the way we can use the influence line diagram for calculating is that we find the position of L by 2 on the IL. Okay, we move up, we find what is the corresponding ordinate, right? So this will be VA at, for the unit load at L by 2, right? So this ordinate value will give the value of VA when the unit load is placed at L by 2. Okay, so from this triangle, it can be calculated, that comes out to half. Okay, so that is so this half is now coming from the influence line diagram, and since the total load applied is 50, we scale it by 50. So if a 50 kilonewton load is applied at the midspan of this beam, the vertical reaction is going to be 25 kilonewtons. Okay, so similarly, one may ask that if let's say 50 kilonewton load is applied at A, right, what is VA? So in this case, we will go to this location at x equal to 0, right? So if the unit load is at x equal to 0, the value of VA for a unit load is 1. Okay, so for 50 kilonewton, it will be 1 times 50, which is 50 kilonewtons. Similarly, we may ask what if a 100 kilonewton is acting at L, which is at point B, then what is VA, right? So again, we can go to point B, right? This is x equal to L point. When the unit load is applied there, the VA for unit load is 0, right? So 0 times the applied load, 0 kilonewton. Okay, so this is how influence line diagram can be used. Similarly, let us say we want to draw the uh, let's look at the trying to draw the influence line diagram for shear force at a location L by 3. Okay, so this L by 3 location, this is a fixed position which is of interest. Okay, so this is a fixed position of interest, and then the unit load, we will consider at a variable location X. Okay, so we can consider different positions in one case. So first case will be when X is less than L by 3, right? And in this case, we can work out the shear force to be minus X by 3, minus X by L. And if we consider a position when this load is just to the left of point C, right, which is this L by 3 minus, the shear force is going to be minus 1 by 3. Similarly, we consider the other case where X is greater than L by 3, right, where the shear force where this unit load is being applied at a location beyond the point of interest. Okay, so in this case, the shear force comes out to minus 1 by 1 minus X by L. And from here, we can evaluate what happens when the unit load is just to the right of the point C. Okay, so that comes out to plus 2 by 3. Okay, so this we have tabulated here, that for which X, what is the shear force at C, right? So for X equal to 0, shear force is 0. For X less than L by 3, it is minus X by L, and so on, right? And using this information, we can draw the ILD. So this is the ILD, right? So ILD for the shear force at C, right? That is this graph. And in this case, now the ordinates will give shear force at C. C is the fixed point of interest. right? And we see the variation from that table, and that we can draw. And of course, this variation is linear because it comes out linear in terms of x. Now, from this ILD, we can, answer questions like, let's say if an 80 kilonewton load is applied at L by 4, what is the shear force at C, right? So of course, a usual method will be to do force balance analysis. But if we have already drawn the shear force diagram, we can consider a location which is here, which is at L by 4, right? So the ordinate here will give the shear force when the unit load is at L by 4. Okay, so that ordinate comes out to minus 1 by 4, and since an 80 kilonewton load is applied, we multiply that. So if an 80 kilonewton load is applied at L by 4, the shear force at C will be minus 20. Okay. Similarly, we can ask a question that if a 150 kilonewton load is applied at L by 2, right, what is the shear force at C? So for this case, we will go to a location of x equal to L by 2, right, and from there we will read what is the ordinate, and that ordinate will be the value of the shear force at C when the unit load is applied at L by 2, right? So that gives this 1 by 2 times 150, so 75 kilonewton is that uh, shear force at C when unit load is at 1 by 2. Okay. Similarly, we can draw, let's say, ILD for moment at a location L by 2, right? So in this case, this location C, which is at L by 2, is the fixed position of interest, and we are interested in a force response, which is the bending moment at C. Okay, and this unit load is at a variable distance x from the left. Okay, and again we can consider two cases: x less than L by 2, x greater than 1 by 2. Okay, and we get a certain expression for the moment, and we can also check that at L by 2 what happens, and then we can come up with the ILD uh, for the moment at C. So bending moment at C. So that is the influence line diagram for that. Right? So the ordinate will give bending moment at C with respect to the position of the unit load along the x-axis. Okay. Let's look at a more sort of a realistic example that so this is a gantry frame or a gantry girder. So this is an arrangement which is used in laboratories or large sheds or industries, to transfer heavy loads from one location to another within a particular shed. Okay. Um, so basically, you know, uh, the load being carried, which is being moved along the girder, right? So this CAB is the girder or the beam, and on this CAB, this trolley or what is called a dolly is carrying a 3 kilonewton load, which is being moved here and there whenever it is needed. Okay, and it is also given that the beam CB has a mass of 24 kilogram per meter. Okay, and the question really is that what is the maximum vertical support reaction at A and the maximum moment at D. Okay, so that is what we want to calculate for all possible positions of the dolly, right, of the 3 kilonewton load. Okay. So basically, we have this type of a picture where the ends A and B are or the locations A and B are pin and roller supported, and there is a 1 kilonewton force which moves from C to B. Okay, now the ILD for vertical reaction at A will be this as shown here. Okay, and now for the maximum VA, right, there will be two loads which will contribute. One is from the weight of the beam, right? Now weight of the beam is not moving, it is a fixed quantity, right? So that will remain constant with respect to location. The second contribution will be from the moving dolly, right? So when the trolley goes from C to B, the vertical reaction at A will change according to the ILD which is shown here, right? So if the dolly is at C, the vertical reaction at A will be 1.33 times 3, and if that is at A, the vertical reaction will be 1 times that, and so on, right? Now, another interesting thing about this ILD is that even when there are uniformly distributed loads, right? For example, in this case, there is a 24 kilogram per meter of load which is acting throughout, right? And if we consider that an individual ordinate of the ILD, that gives the value of the vertical reaction at A when the unit load is acting there. Okay, so basically, if there is a UDL being applied, what is possible is that this entire area, right, that multiplied with the UDL, that will give the value of vertical reaction at A for the UDL. Okay, and this can also be seen by considering a differential element. Let's say if you consider a differential element of dx at x from the left, right? So the vertical reaction at A due to this differential element will be the load intensity, let's say W times dx, right, times the ordinate, which is coming from here, right? And this and when you go from, let's say, C to B, the total vertical deflection will be just integral of this, right? Now this W is being constant will go out, so this is just y dx, which is the area under the curve, right? Right. So for y we can substitute in terms of x and we can integrate, but the bottom line is that is just the area under the curve. Okay. So the first contribution of VA, we will have this is the weight, right? So we have multiplied that by the gravitational acceleration, right? And then this is the area under the ILD, right? So this is the area. Okay, and so this 0.63 is the first contribution. For the second contribution, we would like to place the 3 kilonewton force at a location where it gives the maximum vertical reaction, right? So that is what we were interested. So we will put uh, the dolly at point C because that is where the maximum ordinate occurs, right? So the maximum contribution from the dolly for the vertical reaction at A is going to be 1.33, which comes from the ILD, times 3 kilonewton, which is the load being applied. So that is 3.99. So the maximum reaction at A is going to be contribution of both of them combined. Right? So that comes out to 4.62 kilonewtons. Similarly, we can discuss that what is the situation for maximum bending moment at D, right? D is the midpoint of the system. Right? So the ILD for moment at D can be drawn, right? So this is the ILD for MD or moment at D. And once we have drawn this, again, there will be two contributions. So this is the fixed contribution from weight, and this is from the dolly, right? So the dolly we would like to place at L by 2, right? Because that is the location where it gives the maximum moment at D, right? So 3 times 0.75. This is due to dolly, right? And for the weight, we just have, this is the weight intensity times, we have this entire area. So the negative area we will count with a minus sign, and then the positive area we will consider like that. And then whatever is the total area multiplied by the weight, that will be the bending moment contribution from the weight, right? So from there we get the maximum bending moment diagram. Okay. So like this, we are able to use the influence line diagrams for calculating several things in case of moving loads. Now, that leads us to something called the Mueller's Breslau principle, right? Now, this principle allows us very straightforward construction of influence line diagrams. So, in earlier cases, we are considering different force analysis for different cases. And that is how we were able to make the influence line diagrams. But Mueller-Breslav's principle gives a very, very straightforward way of being able to make the ILDs, at least in the qualitative sense, if not quantitative. I mean, although quantitative is also possible. Okay. So what it says is that the influence line of any force response at a point of the structure is given by the deflected shape of the structure, right, resulting from a unit displacement at the same point. Okay. So if you are interested in, let's say, vertical reactions ILD, we will apply a unit displacement at that location of the vertical reaction, and whatever is the deflected shape of the structure, that will be the influence line diagram for that force response. Okay. So let's look at a very quick proof through the principle of virtual work, and this is really, really straightforward. Let's consider this beam ABC, okay, and let's say we want to make the influence line diagram for vertical reaction at A. Okay, so we want to make ILD for vertical reaction at A. Okay, and let's consider two systems, system 1 and system 2. Okay, in system 1 and in both the systems, we have removed the vertical fixity of the support A, right, because that is where we want to measure. So in system 1, we have removed the vertical support of A, so that reveals the vertical reaction force, right, VA. And on this system, we apply this unit load, right? And the idea is that as this unit load goes from left to right, as x goes from left to right, we will calculate VA, and whatever that variation is, that will be the ILD for VA. Okay. Now we consider a system 2 where we apply a unit upward displacement. Okay. So we apply a displacement in the direction of VA. VA was the force of interest. Okay. So we apply a unit displacement at A. Okay. Now let's consider what happens as a consequence. Okay. So in system 1, because of this load of 1 unit, right, there will be some deformation. Okay. Let's say this figure is giving the deformed shape. Okay, and this VA is not letting that roller go down, and that is where we are getting the reaction force. Okay, so in system 1, this is the deformed shape. At a location X, our unit load is located, and this VA is there. Okay, in system 2, we have applied a delta A upward 1 unit, right, and we can measure what is the distance, what is the displacement at a distance x. Okay, and this x we are saying is same as the x of the first system, right? What it means is that in system 1 and system 2, we are applying a force, a unit load there, and in system 2 we are measuring the displacement at the same point. Okay, so now these are two systems which are not related, and hence we can use the principle of virtual work. Okay, where we say that summation of forces in 1 times displacement of 2 is equal to 0, right? So we have VA, which is force from 1, right, times 1, which is displacement from the second one, right? So these are in the same direction, so there is a plus sign. Then we have this 1, which is force from 1, right, in the downward direction, and then we are measuring this delta x at a distance of x in the second system, right? And since the unit force is downward and this delta is upward, that comes with a minus sign. Okay, and this is the principle of virtual work, and hence we get this relation that VA is equal to delta x. Okay, so what this is indicating is that if we measure displacements in the second system, right, that will be equal to the VA of the first system. Okay, in case of a unit load, right? So whatever is the deformed shape in the second system, that will be the influence line diagram for the first system, right? Because x is going to be the location of the unit load. Okay. So with this, we can relook at the earlier cases, right? So let's say again, we have this simply supported beam, and let's identify 2 points C and D somewhere along the beam, right? Now for ILD at VA, right, if we have to draw, all we need to do is at A, we remove the vertical fixity, and then we displace, we take this roller, we take this roller like that, and we displace it upwards by 1 unit. Okay, so that's what we have done here. Okay. And whatever diagram comes out, so this is the deflected shape of the beam for the unit displacement when the support at A has been removed, vertical support. And this is also the ILD for VA, right, from the Mueller-Breslav's principle. Okay. Similarly, we may look at, let's say, influence line diagram for shear force at C. Okay. So in this case, we will cut the beam at C in a way that they are guided fixed type supports, right? And by due to sign convention, we will apply the displacements in that way, okay, as shown by the arrows. So to the left span, we apply a downward displacement because this is the positive sign convention for shear force, right? And for the right one, we apply upward because that is the positive sign convention for the shear force. Okay, so that gives us this particular shape for the influence line of shear force at C. Okay. Now, one thing to remember in this will be that how to. So this will give a qualitative sense, but if you want to quantify, what we can do is we know that this A plus B will be equal to 1 because the total deformation or the total displacement given is 1. We also know that L1 plus L2 is 3, where L1 and L2 are the so L1 is the location of point C, right, and L2 is just L minus L1. And we also know by similar triangles that A by L1 and B by L2 are same. Okay, so these the slopes are going to be same because for moment we are not doing anything, so we are cutting it for shear force. And this you can relate to the earlier discussions when we were doing it with principle of virtual work for rigid bodies. Okay. Similarly, then we can talk about influence line diagram for moment at D. Right. For moment at D, we will make D a pin, an internal pin or an internal hinge, and then we will move that up so that the rotation angle is 1. Okay, and once we know this rotation angle, then other quantities can be calculated for quantifying. Right? So this simply becomes the ILD for the moment at D. Okay, so this is how we can use the Mueller-Breslav's principle for creating ILDs, and the good thing is that it will work for all types of systems. So it need not be a determinate system. For indeterminate systems also, we can use that. Then if we are interested in calculating, let's say, maximum forces on a structure, right, we would want to place the unit load or the actual load which is passing at locations where it will maximize the total sum, right? And as we saw that for distributed loads, we can consider the areas under the influence line diagrams. So in this way, influence line diagrams are a very useful way of finding maximum forces, maximum bending moments, specifically in cases where there are moving loads like a gantry girder or a bridge where vehicles are passing, etc. So in this way, we can use them.